Okay, here we go again. Principle number 11 is looking at the limit as x approaches c of the nth root of n of x. And as we've seen previously, we're just approaching c, so the limit, we can plug in c for x and get the nth root of c. However, I've added a qualifier. This is different if n is odd and when n is even. So this is true for all n if n is odd, but if n is even, it's only true for positive n's. So I'd like you to think about why that is true. So what are we trying to avoid here when we're looking at if n is even, we're only going to allow positive n's in the expression. Up here, if n is odd, we'll accept all n's, positive and negative. So why do we have to qualify that? I want to know. So I'm going to ask you tomorrow and see if you can remember to answer that. Or if I can remember to ask it. F and g are functions. The limit of g, now this is taking a little different twist, so set up this problem. F and g are function. The limit of g as x approaches c is L. So I took the limit of this one, and then the limit of f of x as x approaches L is f of L. You probably see where this is going, especially since it's right there. It's talking about when you have one function inside of another. What's that called? Have you been well taught? It's a composite function. So recall we always go into the inner court first, and we do the g of x. We would do the g of x function first in this example. But when we have one function inside of another, how do the limits work? I'm sure you're dying to know. So I will keep you in no further suspense. So what happens is, we know the inner court has the limit L, so we just substitute L into the f function, and we're going to get the final answer, f of L. Alright, that is a lot more confusing to see the theory than it is to see it in practice. When you see it in practice, you'll say, oh, of course. Alright, so let's look at one in practice. Say the limit as x approaches, say 0, of the square root of x squared plus 4. The limit as x approaches 0 of the square root of x squared plus 4. This is a composite function. It has the function x squared plus 4 inside another function, which takes the square root of that. So whenever you have a two-step process or multi-step process, you're dealing with composite functions. So do we not have to do this first and then this? So that's composite. So all we have to do is substitute a 0 into the inner function, where we get 0 squared plus 4, and then take the square root of what's in there. So we take the square root of 4, which is 2. So your intuition would have led you there. Your mathematical nose would have taken you to the spot. All right, on the next section, I should have said c is real. So we have a real number c, and we're going to only think about the domain of the trig function that is given. So I'm not going to list all of those. So just assume that we're working in the domain of the function we're talking about. Told you we're going to be rigorous. All right. All right, so the limit as x approaches c of sine of x, you just plug in the c, and the limit is sine of c. Remember, we're approaching c and we're approaching sine c. Limit as x approaches c of cosine of x is cosine c. Tangent c for the limit as x approaches c of the tangent. Let me scoot the view over here. And here, we're going to get cotangent secant and cosecant similarly, and I'll get out of your way. There you go. And we have established 18 theorems in a few minutes. So far, we have been finding limits and by substitution, factoring, and multiplying by a unit multiplier that uses the conjugate of either the numerator or the denominator. So to finish today, I'd like to add another method. So this method is taking a turn from all these. All these is just established the rigor and the background, the foundation for us to use these three. Now we're going to find a fourth one that doesn't really have much to do with what you've seen so far. And that fourth one is called the squeeze theorem. You have also heard it called the sandwich theorem or the pinching theorem. So you can see they all have similar, the gist of it is similar. So let me go ahead then and look at a situation where I can give you the squeeze theorem and prove it and use it. Let me see how much time we've used already on this section. 8 minutes. All right. I think I might, even though it's been 8 minutes, make a third part in case I ask you to actually view this on another day. So I'll make that decision in class. But for now, part 3, it'll be right with you.